SwayamPrabha. Digital India. Educated India.
We will continue our discussions on spatial kinetics of rigid bodies and look at some further problems that will demonstrate the applications of the equations of motion that we have derived in previous lectures. The first problem that we will look at is again taken from the book of Merriam and Craig. It says, determine the bending moment m at the tangency point A in the semicircular rod of radius r and mass m as it rotates about the tangent axis with a constant and large angular velocity omega. Neglect the moment mgr produced by the weight of the rod. We of course, we can have this system, the z axis is vertical, therefore, it will, because of the weight of this semicircular rod, we will have a moment about the y axis, but we are to neglect that. We are to determine the moment that is produced because of the rotation of this bent rod, just because of the rotation. We choose this coordinate frame x, y, z. This frame is fixed to the rotating shaft and aligned like this, that the semicircular rod lies in the x z plane. The rod lies in the x z plane and y is perpendicular to the plane in which the rod is, of course. The moment of inertia tensor for such a rod will have a general representation, but we know because this lies completely in the x z plane, therefore, apart from the diagonal terms I x x, I y y, I z z, we will have the products of inertia that involve x and z coordinates, therefore, I x z, that I have shown. The other products of inertia will be 0. Now, these calculations you must have learnt in mechanics. We will look at what are the terms that will be required. Now, angular velocity vector omega of this system, which is in the z direction, therefore, omega has a representation omega k cap, or in matrix form it is 0 0 omega, and if I multiply this with the moment of inertia tensor about A, I get the angular momentum about A, which is given by I x z omega I cap plus I z z omega k cap. Therefore, we need to find out I z z and I x z about that point A. This is what we need to find out. We will do this calculation. Here I have drawn this semicircular part of this rod. A is at the origin and z axis is vertically upwards, x axis is to the left. I consider a little element of this rod which is shaded in green at an angle theta measured from the horizontal. You should note how theta is being measured. Now, the product of inertia I x z is integral of x z dm. What is dm? Dm is the mass of this little element. Rho, I consider rho as the mass per unit length of this rod. This is a uniform rod, therefore, I can consider a mass per unit length of the rod, and r d theta is the little length of this element. R d theta is the little length of this element, therefore, rho r d theta is dm. And the x coordinate and z coordinates are required. I can find out this x and z coordinates I need this and I need this. These are easy to find out. For example, the z. The z coordinate of this element is nothing but r sin theta, and the x coordinate of this element is r minus r cosine theta. This is what I have written out here, and this mass per unit length I can find out because m is the mass which is given for this rod, m by pi r the length. So, mass per unit length is rho is m by pi r. Now, I have to perform this integral. This integral is straightforward. I get finally 2 by pi m r square, where I have used this definition to eliminate rho. Okay. Then we have to calculate the next element of the moment of inertia tensor. Note that I have found out the angular momentum about A first, and then I note down which elements of the moment of inertia tensor are to be calculated. I do not straight away start calculating all the elements of the moment of inertia tensor. Okay. Then I z z. This is simply x square plus y square integrated over dm, and x and so this is these expressions are written here, and what I do is I perform this integral, and this turns out to be 3 by 2 m r square. This turns out to be 3 by 2 m r square. This is I z z expression. I substitute these expressions in the moment of in the angular momentum about A expression, and I get this as the angular momentum of the ring or the semicircular rod about A. So, this is our angular momentum. Now, omega of the axis of the coordinate frame is omega k cap. Now, moment on the semicircular rod can be determined using this equation m about A. A is a fixed point in inertial space. M about A is equal to rate of change of the angular momentum about A, and we use the prescription to find out the total time derivative, that is del del t of angular momentum about A plus angular velocity of the frame cross the angular momentum about A. Now, there is no temporal change, the magnitude of omega is constant. Therefore, if you just plug in all these expressions that we have found, and we have neglected gravity of course, and we get this expression of moment about A on the semicircular rod, and this is in the negative j cap direction. If you had you included gravity, then on the left hand side you should also add the moment because of gravity, because the net moment about A should be calculated, and one is the unknown moment which is because of the rotation, and to this you should add the moment because of the weight. And if gravity acceleration due to gravity is vertically downwards, then this should be the weight vector and the moment would be mgr. About positive y direction, therefore, mgr j cap should be added to the left hand side. This is the known moment, and therefore, if weight were to be considered, then to this, when you bring the moment due to weight to the right hand side, it will get a negative sign. Therefore, on the rod, semicircular rod, you will have additionally minus mgr j cap moment if you do not neglect the weight. We move over to the next problem from the book of Merriam and Craig. A large balanced antenna has a moment of inertia I about its z axis. This z axis is the axis of symmetry, and a moment of inertia I naught about each of x and y axis. Determine the angular acceleration alpha of the antenna about the vertical z axis caused by a torque m applied about capital Z by the drive mechanism at a given orientation theta. You must have seen antenna of this type used in television transmission or receiving television signals, or in radio telescopes. In telescopes also we have these kinds of antenna, or in communication, for communication. This balanced antenna, by balanced antenna I mean that the center of mass is located at this point. This is just to simplify the whole thing, because had the center of mass been somewhere else, that would produce another moment. Okay, usually such antenna, especially when they are to rotate, they must be balanced, otherwise it will produce, it might produce lot of unbalanced moments because of rotation. I look at the free body diagram. I will consider this x y z coordinate frame which is fixed with the antenna and rotating about that capital Z axis. Now, here I have marked out the moments acting on the antenna. This was our capital Z axis. This vertical was our capital Z axis, and the applied moment, what I have shown as vector m is that applied moment at the base. In addition to that, because the antenna cannot rotate about the other directions, there must be moments in general. Let us see, because to start with I do not know what are the various moments. Now, I have taken a general situation where this capital M is the applied moment, and m1 and m2 are moments which are unknown to me. My equations will tell me what exists or what are their expressions. Let us proceed with this. I will use this equation of angular momentum. H o dot is m o, about that fixed point O, fixed point in inertial space about which this is rotating, and H o is the moment of inertia tensor times the angular velocity vector. The moment of inertia tensor is already specified in this problem. X y z is the principal frame for this body. I naught, these are the moment of inertia about the x and y axis, and I is the moment of inertia about the axis of symmetry. Angular velocity in this frame can be represented as omega cos theta I cap plus sin theta k cap. You have the angular velocity which I can mark here. It will have a tendency to rotate like this. Omega has this expression, and this is the angular velocity of the frame as well. But it so happens in this problem that omega is 0, but I will keep it till the end. Therefore, the angular momentum about O is I o times omega. The rate of change of angular momentum, we follow the same prescription, the local rate of change del del t of HO plus omega frame cross HO. If you do all these calculations, del HO del T is the time derivative of these terms, not the frame, these terms. Here we can have acceleration because this omega can change. Theta is not changing, theta is this angle. Theta is this angle. It was mentioned in the statement of the problem that at a particular configuration, you can relax and try this problem. You can relax these considerations and then try out the problem. Okay. Therefore, theta dot has been considered to be 0 when I take del T. Only omega dot is considered, which is denoted by alpha, and this comes from the frame derivative. So, because of the rotation of the frame. So, the frame derivative term gives me the term, additional term here, and if I proceed with this, on the right hand side I have the net moment about O. Because I have a balanced antenna, the center of mass is at O, therefore, I do not have any gravity any moment due to the weight or unbalanced antenna. Had the center of mass been somewhere else, you would have added that additional term as a moment, as a known moment about O. But we are assuming for simplicity that the center of mass is at O. Therefore, the only moments on the right hand side, the net moment on the antenna are the applied moment represented in the XYZ frame, the moment m1 again represented in the XYZ frame, and moment m2 represented in XYZ frame. We proceed with the calculation. This is the I cap equation, this is the I cap equation, then we have the J cap equation, and finally the K cap equation. Let me mention this, this is I cap, this is the J cap equation, and this is the K cap equation. I have these three equations coming out of the angular momentum equation, and I have three unknowns. I have angular acceleration as an unknown, I have m1 as an unknown, and I have m2 as an unknown. So, there are three unknowns: angular acceleration, moment m1 and moment m2, and there are three equations I should be able to solve. You will note that since the angular velocity is 0, I mean it was mentioned that a moment m is given to the antenna, and we have to find out the angular acceleration. Initial angular velocity is not mentioned, so maybe it is from rest. If it is from rest, then you will find immediately if omega is 0, then m2 vanishes. There is no net moment about m2, but this is only at the time t equal to 0 plus when the moment was applied. As the antenna starts to rotate, omega 2 will generate and you will have moment m2 in the y direction. Okay, this is only for time equal to 0 plus, but just after that moment has been applied, but antenna has not started rotating. Let us proceed then. I use the equations 1 and 3. I multiply 1. See, I have simultaneous equations 1 and 3 in alpha and m1. These are the two unknowns. Simultaneous equations 1 and 3 I solve. I multiply 1 by cosine theta, 3 by sine theta, and I add them, and what I get is alpha. I can solve like this m1, I can, of course, m2 is directly available from the equation. Therefore, this is the angular acceleration that we will have. at time t equal to 0 plus, because there will be if you consider, for example, if theta is changing etc., then you will have more complicated, more terms, and the analysis becomes more complicated. Let us move to the third problem, again from the book of Merriam and Craig. Two identical circular discs of mass m are welded to the two ends of a rigid rod of mass m naught at an angle such that the discs have a common z axis. You can see from the figure, this is a very special connection. In the figure that has been shown, the rod is in the x z plane, the rod is in the x z plane, and the two ends of the rod are attached to the two discs in such a way that there is a common axis of symmetry for the two discs. The rod is of course at an angle with z. Now, these discs are separated by a distance b, as shown. A couple moment m applied to one of the discs with the assembly initially at rest gives the combined mass center g and acceleration a along the horizontal direction shown. Determine the normal reactions n a and n b on the discs from the ground in terms of the acceleration a. Now, the figure is a little complicated here, it is a full 3-dimensional figure, and you can, and this isometric view gives you only a particular viewpoint of that figure. But as I mentioned, right now the rod is in the x z plane and the center of mass of the whole system is at the origin. So, this x y z frame is at the origin of the x y z frame's origin is at the center of mass, and upon this application of this moment m to this disc on the right, we have an acceleration, horizontal acceleration a. We have to calculate the normal reactions n a and n b under these two discs at the points a and b in terms of the acceleration a. We will use this coordinate system x y z. I have fixed this x y z with the system, which means as the assembly rotates, x and y will change directions. This is to make the moment of inertia tensor constant in the chosen frame. I have also drawn a top view of this assembly, and this also marks the forces, different forces that are acting. So, this can be considered to be the free body diagram. It is a full 3-dimensional free body diagram. We have forces in various directions. We have the applied moment, shown here. It is in the negative z direction. We have the friction forces under these discs F A and F B. The normal forces I have shown by this convention, normal reactions from the ground, they are perpendicular to the plane of the screen and coming out of it, therefore, a circle and a dot. This is N A, this is N B coming out of the plane of the screen, and the weight which is going into the plane of the screen. The weight is going into the plane of the screen, that should be marked by a cross, not very clear here, and that force is minus of 2 m plus m naught g j cap, 2 times the mass of each disc plus mass of the rod times acceleration due to gravity. And the acceleration that this assembly suffers is in the horizontal direction. I will write the equation of motion of rotational dynamics using the center of mass. The rate of change of angular momentum about the center of mass is equal to the net moment of all forces about the center of mass. I will first calculate the moment angular momentum about g. For that I need the moment of inertia tensor of the whole assembly. First I have written down the moment of inertia tensor of the wheels. There are two wheels, moment of inertia tensor. Now here I have used the parallel axis theorem. I know that about its center of mass with this coordinate system I have mr, half mr square, half mr square and mr square, and there are two disks and there is a shift, a parallel a shift in the z direction. Therefore, I have these additional terms. So, this is 2 times half mr square, this is Izz, that is how I get this. This Ixx is 1 by 4 mr square plus m L square. L square is the shift, L is, I have written out, L is b by 2. Now, this must be multiplied by the factor 2, and that is how I get this Ixx and similarly Iyy. For the bar, I have this general expression, the mass is distributed in the x z plane. Therefore, I have, apart from the moments of inertia about x, y, z, Ixx, Iyy, Izz on the diagonal, I have these two off diagonal terms. Since mass is distributed in the x z plane, I have the products of inertia Ixz. We will calculate, okay, so angular velocity vector is in the z axis direction omega k cap, and that is also the angular velocity of the frame. Now, moment of inertia, so the angular momentum about g is moment of inertia tensor times angular velocity, and that turns out to be this. Now, I note which terms I have to calculate. For the bar, I have to calculate Ixz and Izz. Now, these calculations can be done in a similar manner as I have demonstrated. Now, rate of change of angular momentum about g, now I start differentiating this, follow the prescription that we have. I have this is constant in the frame that we have, it is fixed to the body. Therefore, I have this time derivative of this alpha, then this is constant, this is constant. So, time derivative of this again an alpha plus omega of the frame cross. So, the frame derivative. So, omega of the frame cross Hg, and that is this last term. Having done that, I calculate the product of inertia and the moment of inertia about z axis. Now, I am ready to apply the equation of motion for rotational dynamics. This is Hg dot, and that must be equal to the net moment acting about the center of mass. What are the moments acting? One is the applied moment, of course, in the negative k cap direction. Because of the friction force and the two discs, we have moment about again k cap direction. Because of the normal reaction, we will have moment about the x axis, and this is another moment that is because of the unequal friction forces on the two discs, and that is about the y axis, which is perpendicular to the plane of the screen here in the top view. Therefore, from the I cap equation, this is the I cap equation. This is the I cap equation. I have a relation for n b and n a in terms of the angular acceleration and the parameters of the system, and this turns out to be minus 1/3 m o the acceleration. I have written alpha in terms of the linear acceleration of the center of mass. From the translational dynamics, if I look at the translational dynamics or Newton's second law for the center of mass in the vertical direction, that means along the y direction, since there is no acceleration, it is only balance of forces in the y direction, and that gives me 0 equal to the sum of forces in the y direction, n a, n b, and the weight. So, I have two equations in terms of n a and n b, simultaneous equations I can solve the straightforward solution. So, I will leave it to you. So, this is these are the normal reactions at A and B. Now, this is the summary of what we have discussed. We have looked at some problems and applications of the equations of motion for spatial kinetics of rigid bodies. With that, I will close this lecture.